everyone, welcome. It's great to have you here today to learn about the scientific method. To start off, I would first like you to focus on this magician, and I have 3 questions for you here. Please look over these questions, and these are questions that I would like you to address before class the next day. First question, if you see a magician make a rabbit disappear, can you trust what you've just observed? And if you can, or if you can, doesn't matter, how could scientific methods help you determine what actually happened to the rabbit? Third question is performing a magic trick scientific? If you can answer each of these 3 questions, you have this lesson mastered. Well, I'd like you to think back to your experience with science before taking this class. Can you describe any methods you conducted the research that help you answer question number 2? You might have recalled setting up experiments, posing hypotheses, making observations, and collecting data. Well, if these words sound familiar to you, you have a pretty good understanding of the scientific method. This lesson is going to go a step further, and hopefully you'll come to a new understanding of how biologists view the way research should be done. But before we start, I got a quick little summary video here for you that's going to address a misconception a lot of students have of the scientific method. And that misconception is that they think the scientific method is just a linear process, which means you have a start and a finish and there's no jumping in between. Well, in actual fact, scientific method is not linear in most cases. It's fluid. They're all designed around a testable question, but you can move back and forth. And the best way to show that is to look at this, watch this movie real quick.
The way scientists answer questions is through an organized series of events called scientific methods. There are no wrong answers to questions, only answers that provide scientists with more information about those questions. Scientists form hypotheses based on questions, observations, and collected information. When drawing a conclusion, the hypothesis will be supported or not supported.
This is where it's not a linear process.
Repeat the experiment many times until results are consistent. If the hypothesis is
You can
not
see
supported, refine and
it's
test
going to
an
form a
alternate
circle.
hypothesis. When the hypothesis has been accepted, it leads to additional experimentation based on accepted hypothesis.
So you notice it's not just linear. That's something very important I want you to understand and keep that in your mind when we continue through this lesson. Well, when we look at it, the actual methods, and I'm going to go through this very quickly, and I'm going to use an example of nitrogen in cornfields as our experiment. In step 1, the first thing you need to do is ask really good questions. And these questions have to be testable, so you got to word them in a specific way. For example, you're going to form your question, and then you're going to make observations. And those observations you want to have as direct methods of obtaining information. Now, a good question could be like this. What's the effect of extra nitrogen on plant growth? Right, that question's realistic, and it's testable. Specifically, if you're a farmer, you can easily see the effects of extra nitrogen on your farm field. Well, once you've made some basic observations, you want to go ahead and make some inferences. Well, what an inference is, it's taking what you know previously with what you just learned from your observations and making a logical conclusion. A really good example here to paint a picture for you is, let's imagine, everybody knows what a bald eagle looks like. It's a big bird of prey. Large talons, big beak, big bird. Well, let's say you go down to New Zealand, and there you see a similar looking big bird. Okay? Maybe it's the Harpy's eagle. And you notice it has a huge meat-tearing beak and huge claws also, just like the bald eagle in America has. Well, if you take your previous knowledge and mix it with your observations of the Harpy's eagle, you can come up with some logical conclusions or inferences, such as you can infer that those 2 eagles, even though they're separated, must have some type of relationship. They must be related in some way, shape, or form. Once your question is formed, it's now time to start making your hypothesis. Now, this is more than an educated guess. It's a testable explanation of a situation. And we always want to write it as an if-then statement. In our case, we'll use if extra nitrogen is added to a cornfield, then the yield of the corn will double. Very good, clearly defined hypothesis with things to measure. Well, you need to be aware, though, when you make a hypothesis of an action called serendipity. And this serendipity means, oops, sorry about that. Serendipity just means you get a good result because you made a mistake. In our case, testing nitrogen on a farm field, maybe I put a little too much nitrogen on my field, and the corn crops just skyrocketed, way higher than double the yield. Well, that's a mistake, but it's a mistake in the good sense, and that's called serendipity. Penicillin was another serendipity moment in history. Alexander Fleming was testing growing bacteria in petri dishes, and he left them in the sink too long, and fungus was starting to grow on them. And when he came back, he realized, hey, this fungus stopped the growth of a lot of bacteria. So he purified it, formed it into pills, and we had our first antibiotic, penicillin. Total by mistake. Experiment didn't go the way it's supposed to, but it went out for the better. That's serendipity. Now, once you have all that formed, the question, the hypothesis, you now get to set up your experiment. And in setting it up, you want to have a control group and an experimental group. The control group is the group that does not have anything done to it, and it's compared. The experimental group is the group that is going to be tested. In our farm field example, let's say I split the farm field in half, and one part of it acts as the control group. I just treat it like normal. The experimental group is I add double the amount of nitrogen. Well, that's the group I'm looking at. Well, once we have the settings set up, now we can see what type of data we want to collect. And the first type of data we want to collect, or we could collect, sorry, is called quantitative. Quantitative means numbers. Quantitative, quantity. It's anything that deals with numbers. Your data could also be qualitative. What does it look like? You're not measuring direct numbers, you're measuring what's the quality of the data. Such as, oh, the corn cobs all look brown. Corn cobs all look white. Okay? That's qualitative. Once we have those addressed, we want to address the variables. And this is where it gets really difficult in an experiment, because you can only have one independent variable. And this is the variable that you changed. In our hypothesis, what we changed was the amount of nitrogen. And what we're measuring would be referred to as the dependent variable, the corn height, or the corn production. You can only ever have one independent variable. Once we have that done, we start collecting our data, our results, we start making the graphs and the charts, and that's all dependent upon how we set up the experiment, which is dependent upon the hypothesis. At the end, we form a conclusion, and we either state whether the hypothesis was accepted or not, and then we go through, we publish it and have it peer reviewed. In science, researchers are never paid unless they publish. And to be published, they have to be what's called peer reviewed. You want your friends and your colleagues to look at your work and rip it apart to find any mistakes. Because it's better to find mistakes then in peer review than after it's been published and other people start looking at it and can think you are completely off in left field on your results. You don't want that to happen. Okay, ladies and gentlemen, that's it for today. That's exactly 10 minutes. Thank you very much for listening, and I hope to see you in class the next day. Have a good one.